Section 2 is Brønsted Lowry acids and bases. You will be able to identify conjugate acid-base pairs for Brønsted Lowry acids and bases. According to the Brønsted Lowry theory, an acid donates a proton or a hydrogen ion, and a base accepts a proton. Free hydrogen ions do not exist in water. The hydrogen H+ ion is so strong that it bonds to a water molecule and it forms what we call a hydronium ion, which is H3O+. If you think about it, H2O right here is a neutral compound. And if you add a proton to it, or an H+ to it, you then have 1, 2, 3 H's. And if you had a neutral compound and you add a plus to it, it now has a plus charge. A solution of hydrochloric acid forms when H+, a hydrogen ion, transfers from hydrogen chloride to water. Water is acting as a base in this reaction, so HCl is hydrogen chloride, or we know it as hydrochloric acid. Since this is an acid, acids are proton donors. So this hydrogen wants to transfer to the base. Bases are proton acceptors, so water is acting as a base, which is H+ acceptor. So over here on my products, H2O becomes H3O+, and we know that H is a +1 and Cl is a -1 chloride ion. It's by itself. Let's look at Brønsted Lowry bases. Ammonia we know is a weak base. It reacts with water, and NH3 is the base. Bases we know are proton acceptors, so it accepts an H+ from water. In this case, because we know ammonia is a base, water can act as an acid. So it would donate one of those two hydrogens. So I'm just going to circle this H. It will donate it to ammonia. So instead of NH3, my product will be NH4. Again, my NH3 was neutral. If I add a plus to it, it now has an overall plus charge. So that is called an ammonium ion. And H2O, since I lost an H, so I'm going to write water HOH, that's H2O. That H is given there, so I'm left with OH. It was neutral, I lost a proton, so now I have a negative charge, which is a hydroxide ion. If my product includes hydroxide, we have a basic solution. If my product includes a hydronium ion, it's an acidic solution. According to the Brønsted Lowry theory, a conjugate acid-base pair consists of molecules or ions related by the loss of one H+ ion by an acid and the gain of a H+ by a base. Every acid-base reaction contains two conjugate acid-base pairs because that hydrogen ion is transferred in both the forward and the reverse reactions. If we go back and look at this last example, here's what I like to ask myself. Okay, which one of the reactants, let's just pick a reactant. Let's start with NH3. Which one of the products is most similar to NH3, but it either gained or it lost a hydrogen? Well, that would be this guy, the NH4. So this would be a conjugate acid-base pair. Now we need to label it. Which one's the acid, which one's the base? Well, the reactants always have an acid and a base, and the products always have the conjugate acid and base. So I'm just going to write C for the right side, conjugate acid and the conjugate base. So how do we tell which one is which on the left side and the right side? These we said was a pair. Which one has more hydrogens? The one on the right, right? So that is my acid, and since it's on the right, we call it the conjugate acid. So that's this guy, which means the ammonia is the base. It's not any conjugate or anything. The left, remember, is just either acid or base. So the ammonia in this case is the base because it has one less H. Let's find our other pair. Our other pair must be the water and the hydroxide. The difference between those two is simply one hydrogen. So I'm going to connect these two. This is our second conjugate pairs. Who has more H's? Well, the water does, right? It's H2O versus this one is just OH. So my water is the acid, which means the one on the right is the conjugate base. Again, they're always acid-base pairs. On the left, we have acid and base. On the right is the conjugate acid and base. So we just have to connect which one has more hydrogens. That is the acid. Because the overall reaction of HF is reversible, the conjugate acid, H3O+, can donate an H+ to the conjugate base, F-, and reform the acid, HF, and the base, H2O. Using the relationship of loss and gain of one hydrogen ion, we can now identify the acid-base pairs as HF and F, along with H3O+ and H2O. Again, this is one pair. The only difference is that this guy has more H's. This guy doesn't have any H's, so it donated that hydrogen ion. The difference between these two, H2O versus H3O, this guy has more hydrogens. This guy is the acid. Here I have hydrofluoric acid added into water to give me F- and H3O+. Again, who is the paired one to HF? Well, over here, F. Those are very similar. The only difference is that we have more H's on the left, so that is my acid. So on the right must be the base, and since it's a product, we say it's its conjugate base. The other two, again, H2O and H3O, this has more H's, so it's the acid. Because it's a product, we call it the conjugate acid. Therefore, on the left is my base. Here we have the ammonia reaction. Again, ammonia and its pair, that's a product that has one more hydrogen, is NH4+. So this is a conjugate acid-base pair. This guy would be the conjugate acid because it has more hydrogens. So NH3 is our base. Our other pair is H2O and OH. On the left, the water has more hydrogens, so it is my acid. On the right is my conjugate base. You saw in both of those that there was water. And in one example, we saw water was acting as a base. In the other example, water was acting as an acid. Water can act as an acid or a base. Substances that can act as both acids and bases are called amphoteric or amphiprotic. For water, the most common amphoteric substance, the acidic or basic behavior, depends on the other reactant. Water donates hydrogen ions when it reacts with a stronger base, and it accepts hydrogen ions when it reacts with a stronger acid. So here I have water. If it's acting as a base, that means that it is a proton acceptor, so it would gain an H. If it acts as an acid, that means it's a proton donor, so it's giving away one to give me OH-. HCO3-, if it acts as a base, that means it's a proton acceptor, so H3O- can become H2CO3 with no minus, because gaining that proton takes away that -1 charge. So it gained an extra hydrogen. We can also take HCO3, and if it acts as an acid, get rid of that H, it leaves me with CO3, and instead of a -1 charge, it's a -2 charge. We know this is carbonate. So that's another example, bicarbonate, of an amphoteric substance. Let's look at the sample problem. Identify the conjugate acid-base pairs for this reaction. Why don't you pause the video and see what you can find? Well, let's look for the pairs. I'm just going to start with HBr simply because it's listed first. HBr. Now let's look at the products. Is Br most similar or is NH4 most similar? Well, hopefully you're able to go, oh yeah, Br and HBr are very similar. The only difference is on the left we have more hydrogens, one more H. So this must be my acid, and I'm going to connect them. This is my first acid-base pair, and therefore on the right this must be my conjugate base because the acid is on the left. So therefore, this must be my second pair, NH3 and NH4. Very similar. One has more hydrogens. Which one has more hydrogens? The NH4+. So that is my acid. And because it's on the right, it's the conjugate acid. So its pair is the base. Hopefully that makes sense. Take a minute to look over the review and make sure that you understand the learning goals and that you are able to identify the conjugate acid-base pairs for Brønsted Lowry acids and bases.